We're going to look at how phase changes operate, and just a quick little review and a little reminder of what intermolecular forces are. They're these temporary attractions, and there's different strengths of these attractions. Some of them have stronger attractions, some have weaker attractions, and those attractions are effectively what allows a state of matter to be that state of matter. And you can see right here in this little third mini section right here, the higher the intermolecular forces, the stronger the attractions, so that if you have high intermolecular forces, your boiling points are going to be higher, or your freezing points are going to be higher. That's because the kinetic energy changes that occur and how they might interrupt intermolecular forces are going to effectively represent how strongly they're attracted to each other. So a substance that will generally have, and this is one line that's worth repeating too, a substance that has the same amount of IMFs is going to be present in all states of matter. So pretty much any state of matter, no matter what it is, the amount of IMFs that are present is going to be the same. It's just that the kinetic energy involved, right? When you have gases versus solids, it's just the kinetic energies are going to kind of or really dictate how much effect the intermolecular forces can have. So solids, the intermolecular forces have a lot of effect. For gases, intermolecular forces have a practically negligible effect, but the amount of intermolecular forces that are possible are still the same. Little review for the terminology. I don't know that this is particularly new stuff, but when it comes to phase changes, there are specific terms going from a solid to a liquid, liquid to a solid, so on and so forth, has terms. The two that are probably the most unfamiliar anyway are going from a solid straight to a gas, right? This is where solid doesn't go through the liquid phase first and then goes to a gas. This goes straight from a solid to a gas. The term we use there is sublimation. More often than not, the most common examples we see are, for example, dry ice becoming CO2 gas. If you ever see a sample of CO2 as dry ice anyway, you never really see it become a liquid first and then become a gas. It just goes straight on through. And that also, same pattern occurs when you talk about having maybe perhaps ice or like in your freezer. So a lot of times ice cubes, when they freeze, will tend to actually vaporize in the freezer. And over time, sometimes the walls of your freezer will actually collect some of that vaporized ice or vaporized water. The other one that tends to be one that is unfamiliar is this one right here, is a gas. That's a very poorly drawn star. But the gas here, going from a gas phase to a solid, that's not much better, is actually called deposition. Right? It's kind of a fancy term, but really it's just saying it deposits on the surface of things. So water vapor may be going straight to ice in this example given here. In that same way, for example, on cold mornings, typically when you go outside and you see the windshield on your car is covered in a thin layer of ice, or maybe sometimes even worse, a thick layer of ice. The reason that the ice appeared isn't because, there's like a thin layer of water that was sprinkled all over your windshield and then it froze overnight. It's because there's a lot of really cold water vapor in the air, and then when it makes contact with the windshield, it gets stuck. So the vapor goes straight from a gas, a vapor form, into a solid ice form that you then have to scrape off the next morning on your windshield. Dynamic equilibrium is a concept that basically revolves around two opposing processes, but the idea is that they occur at the same rate. So it looks like there's nothing happening. It looks like from the surface of what we can observe as with our eyeballs and such, it looks like nothing's happening. But in fact, on the particle scale, both opposite processes are happening. For example, if I were to take rubbing alcohol and put it inside an empty bottle, if I seal it off, at first, you're going to see basically a lot of vaporization occur. A lot of the particles of ethanol or rubbing alcohol are going to go from having the liquid particles down here, right? And then it's going to start to vaporize very rapidly because, that's what happens when there's no vapor there. It's going to be allowed to vaporize. But then after a while, some of these vapor particles are actually going to return right back into the liquid phase. So some of these are escaping and some of these are vaporizing. And so over time what's going to happen is that the rate of vaporizing and condensing are going to be the same. But to us anyway, it looks like nothing's happening. If we had a pressure sensor in there measuring all the pressure that's up here, that pressure would look constant. It would look unchanging, but just know that on the particle level, there is definitely a dynamic equilibrium of escaping and returning back to the liquid phase. So that rate of vaporization equaling to the rate of condensation, again, that is called an example of dynamic equilibrium. Here's a little visual again, kind of maybe one that's a little bit more pretty, and less haphazardly drawn like my previous one. But again, let's say we have a liquid in here that we start with. In this case, it ends up being water. At first, there's no water vapor in here, right? You immediately pour it in, and then you immediately seal it. There's nothing up there, right? There's no particles of anything up here. And so what happens is that the water vapor will quickly start to vaporize. But then in the middle section right here, you kind of see that while there is some vapor again appearing up here, at the same time there's some that's returning back. That's just a natural process that occurs of condensation. And then over time, again, it starts to reach a rate at which both of them they vaporize and condense at the same rate. So therefore, you've reached a equilibrium. This one is an example of dynamic equilibrium when you talk about vapor and liquid going back and forth to each other at the same rate. So the specific thing we're going to get into here is called equilibrium vapor pressure. So this is what I mentioned earlier, right? So the vapor is, again, these particles of a liquid that are normally a liquid at room temperature. That's a large majority of its constituency. But when you have a situation now where you actually can kind of measure the vapor particles that are above a liquid, that vapor particle pressure is called vapor pressure. So this, again, is only measured, can only really be truly measured after equilibrium has been met. Now, that kind of makes sense then that we can actually alter vapor pressure. So when you take a look at a sample of a liquid and look at the vapor that it might generate, or the vapor that it's resting above the liquid, you can actually make some predictions. So right here in the middle, let's just say that this is some temperature, doesn't really matter what it is, and you have a certain number of particles floating around up here. I believe there's about 11 of them. And so when you take a look at this, right, you can then heat up the sample of the liquid, and then you can maybe make predictions about what kind of particles are up here. Well, for those of you who might be making some predictions about this, you'll notice that actually there should be a lot more, not a lot more, but there should definitely be an obviously increased number of particles that are in the vapor phase, right? Because the warmer they are, the more kinetic energy these individual liquid particles have. Therefore, they're more able to escape into a vapor phase. So when you heat it up, eventually it's going to reestablish its equilibrium to where there's going to be a lot more vapor particles up into this space than there were before. Because the individual particles have now increased their energy, and so they've been able to escape more readily. Right? So the vapor pressure in this container to the right, when it's warmer, will definitely be higher, right? Higher than at least what this one is. On the other hand, if you were to cool down your sample, right, the individual particles are not able to move as fast. They're not going to, again, be able to generate as much vapor pressure because there's just going to be fewer vapor particles. They're not going to be able to escape as readily. And so more particles will be in the liquid phase rather than the vapor phase. Of course, now talking about intermolecular forces and kinetic energy, right? Intermolecular forces are always present in some way, shape, or form. And so if your particles don't have enough energy to escape from those intermolecular attractions, then it's not going to be a liquid, right? It's going to remain a liquid. But if it has more kinetic energy, it can potentially escape those intermolecular forces, which is why, again, you see more particles up in this phase than you do down here. Of course, even though it's not being shown here, it looks like it's a static image where this is pretty much the only particles that are going to be vapor. But remember, at any given moment, you do have that process of particles not only escaping, but also returning back in liquid form. So now we can compare vapor pressure to different liquids, right? So different liquids can have different equilibrium vapor pressures. So this chart right here, if you notice, there's a couple of features that you have to pay attention to. First of all, the pressure of the vapor, which is listed right here on the left in torricelli's. And then down here at the bottom, these are temperatures. So you have three different substances: diethyl ether, ethanol, and water. And we're basically going to look at them and see how their vapor pressure changes. Now, before I actually get into the specifics of the questions there on the left, notice a couple things. First of all, as you go from left to right across the x-axis, the temperature is going up. Well, what do you notice happens to the vapor pressure? Well, that also increases. That's consistent with what we predicted in the previous slide, with more and more vapor particles appearing in equilibrium as the temperature increases. Now, let's go and address the questions here. At 20 degrees Celsius, which liquid experiences the highest vapor pressure? So at 20 degrees Celsius, we're going to isolate this temperature right here. So going up through this one, which one experiences the highest vapor pressure? Well, that means diethyl ether is way up here, so that means diethyl ether will have the highest vapor pressure at 20 degrees Celsius. Now, the other two, again, they definitely have some vapor pressure. It's just significantly lower at that same temperature. Number 2, at any given temperature, which liquid experiences the highest vapor pressure? Well, again, it's kind of the same idea, right? If I just drew a vertical line at any temperature, right, say this one right here, which is going to have the highest value? Which one of these gases, or which one of these liquids will end up having the most vapor? And that's going to be, of course, diethyl ether. That one consistently rides along the top here, and even though it runs off the chart, you can kind of imagine it continuing projecting on to also remain the highest. So then, what conclusion can you make about the relative IMFs in comparing these three substances? So diethyl ether versus ethanol versus water, which one of these has the greatest amount of intermolecular forces between them? Now, of course, you could go through and look at the particle structure and the Lewis structure of diethyl ether versus ethanol versus water and make the same conclusion. But I think using some data, some hard data that we can observe, that also helps us justify and help us reason that what we decided or what we can determine is also consistent. So let's try this out. Diethyl ether at any given temperature has really high vapor pressure. So that means the amount of attraction the particles have to each other so that they remain a liquid is fairly low. Right? Because that means at this cooler temperature, let's say 20, at 20 degrees Celsius, that means these particles already have enough energy to escape to become a vapor. Right? That's why the vapor pressure is so high. Therefore, you can predict that the IMFs of diethyl ether is going to be fairly low. Compared to water on this side, right, at 20 degrees Celsius, the vapor pressure is very low because not a lot of particles have enough kinetic energy to escape. Generally speaking, water and diethyl ether have the same kinetic energy, but for water, it doesn't have enough to escape its IMFs. So you know that water has much higher IMFs compared to diethyl ether. So the order, again, if you look at the IMFs in general, diethyl ether is the lowest, ethanol is somewhere in between, and then water would have the greatest amount of intermolecular forces. Hopefully you started acknowledging the fact that water, again, almost always has the highest amount of intermolecular forces when we compare substances. Volatility, this is a term that describes basically how well a liquid will vaporize, how well a specific substance will vaporize. So it kind of makes sense that the more the IMFs you have, the less volatile they are. Right? So the more intermolecular forces they have, the less likely they are to vaporize. And that kind of makes sense because the more intermolecular forces, the stickier the particles are to each other, so that means they're a lot less likely and a lot less able to escape. And so in this context, right, it kind of makes sense that some things are described as more volatile, some things are described as less volatile, and we can make that conclusion about their IMFs. Vice versa, we can also make a conclusion about something's volatility by looking at their IMFs. So which of the three substances from that previous slide, that diethyl ether, that ethanol, and that water, is the most volatile? Right? Which one is most readily able to escape? We made the conclusion that diethyl ether, right, I'm just going to abbreviate that well, probably don't want to just do that. Let's try this again. Let's abbreviate that diethyl ether with DE. That one is going to have the least amount of intermolecular forces available. Therefore, it is considered the most volatile because it's most readily able to escape. Whereas least volatile, on the other hand, is water. Water is going to maintain its liquid form as much as possible because, generally speaking, most particles don't have enough energy to escape. Substances that do not vaporize readily are described as non-volatile. So these are substances where the intermolecular forces are so strong that they don't even vaporize at all. Some of those examples you might maybe imagine are things like oils, right? Oils, or maybe even perhaps waxes. Now, some of you may be thinking, well, my candle is made of wax. I can definitely smell and vapor. The stuff can vaporize really well. That's a little bit different, right? Because waxes themselves actually are not very volatile. You're probably just kind of smelling the scents that are embedded within the wax, but it's not the wax itself that's vaporizing. So another example to kind of talk about this too is thinking about, like, for example, gasoline, right? If you've ever been to a gas station and filled up your own pump, generally speaking, there's almost always going to be a couple of drops of gas that tend to fall out of the end. Well, unfortunately, those gas particles, right, we can't really save and use, and of course are not really great for our environment, but those gas particles, one of the things that's nice to observe about it is that they vaporize very quickly. They actually hit the ground, right, whenever you pull it out of the gas tank, hit the ground, and then almost immediately they seem to disappear. And it's not that they just kind of went nowhere, it's that they quickly became a vapor. So gasoline is something that's considered to have high volatility. Not because, again, it can go boom really readily, but because it vaporizes very quickly. This last bullet point here, a small amount of each substance of the following were spilled on a lab bench, which would evaporate the most rapidly. So looking at diethyl ether, ethanol, water, and candle wax, which you saw again, if you spilled those again onto a countertop, you'd expect that diethyl ether will evaporate the most rapidly. It is the most volatile. It has the least amount of intermolecular forces available. And that'll do it.